So thanks a lot for the introduction. I'm really happy to be here because I'm really interested in interdisciplinarity, not only because of my background, but also because of what I study right now. This is AI fairness and safety, and I think there are a lot of links with social sciences here. So I will give a quite broad overview, and therefore it will be quite high level, but I think with some concepts you are familiar, so I hope I will be able just to draw the connecting dots between the things. So for the purpose of this talks and the links that I want to draw between social sciences and AI, I categorized machine learning or AI into 3 categories, which is very rough, but nevertheless I think it will be useful for our purposes today. The main axis for categorization is what those models actually do. So by ML models, I mean the prediction models that do either regression or classification problems, and what is right now referred to as classical models. Whereas generative AI can generate image or text, and LLMs can fall into this category as well, depending on the task that it is given. And the most controversial probably is the agentic AI part, because there are lots of definitions. There are also, there's no reached consensus what it is, but usually you think about something that is using tools, has tasks and goals. But what I want to pay attention to the most is the interaction. So the same LLM model can be agent in a sense if it is interacting with humans as a chatbot, or if it is interacting with other agents in multi-agent system, let's say. And the social sciences are important across ethics and safety challenges following this line. What I want to show is that it gets even more interesting as we go further through this development. So first of all, what is social science? I just took a very broad definition that it is the study of people, individuals and communities, and a lot of things fall into this category: economics, political science, history, sociology, psychology and anthropology. But I specifically exclude the neuroscience here, even though neuroscience sometimes referred to as behavioral science and clearly is a science about humans. And it has a very interesting feedback loop with mechanistic interpretability research in AI, but therefore it's so rich and interesting, it just falls out of the scope of this talk today. So I'll start with prediction and machine learning algorithms, and I'll remind the fairness problems that have been noticed early on as they were deployed. Those algorithms were used in image recognition, in predicting priority healthcare access, hiring tools, also predicting criminal reoffense, and they have shown racial, gender bias, basically bias to minorities or historically disadvantaged groups. Here's also an image of coded bias, because this topic even led to documentary in Netflix, so it's quite well discussed already. And it also led to a discipline, fairness in machine learning. When you think of this discipline and how it even starts approaching why algorithms can be unfair and what can be done of it, we are already seeing that social sciences play a big role here. So first of all, what are the social determinants in the first place, like gender, race, social economic status, what could influence associations in the data, and what is fair? How does justice look? From history, we can know about what historical inequalities were present during the ages, and also how it could have more recently influenced the collection of the data and therefore misrepresentation or underrepresentation of certain groups. And cultural anthropology, where I originally come from, looks at the cultures and how cultural contexts influence how people behave and evaluate things, and this can lead to the situation where variables predictive for one cultural groups are not so predictive for others. For example, the use of banking operations versus cash is very culturally dependent, and it's also an important variable in credit scoring. And when you measure and evaluate fairness and define what is fair or not, you mainly encounter two worldviews. This was distinguished by a famous paper by Friedler et al. And how you look at it depends on where you stand in those two worldviews. So the first one says we're all equal, and some variation is normal between individuals, but the groups essentially should have equal results, and if they are not, this is due to structural bias and it should be corrected. And the other approach says what you see is what you get, and we have data, it reflects objective processes, and therefore we need to use it to make predictions. Connecting to mathematical notions of fairness and ways to measure it, it's possible to associate the first worldview with statistical parity, which requires the probability of positive outcomes to be equal for sensitive attributes. So S would be a sensitive attribute like gender or race. For the second worldview, even though it's not how it's canonically associated, but you could say that equal opportunity measure would make sense because it requires the outcomes for the groups to be equal, but given the ground truth label. So if the label in data says that the outcome should be positive for this group, and the algorithm also predicts so without introducing further bias, which means that it's fair, it is reflecting the reality. Both of those approaches have both advantages and disadvantages. So one advantage that it can be estimated from the data, and it's easy in this way. And disadvantages is that the first one can really impact negatively the accuracy, and sometimes just doesn't make sense at all why the outcomes should be really equal. And the second one also has a pitfall, because those labels, why we are relying on, they can actually be biased either by individual decisions or by structural biases. So can we find some way to reconcile those opposite directions? And I think to some extent we can, if we ask the questions on what caused the bias, how did it come into being in the first place? And this is a causal question, essentially. So I want to give an example of a case where causality is important, and answering those questions is important to really evaluate what's happening. So this is Berkeley admissions paradox. I think probably most of you have heard of it. It also corresponds to statistical Simpson's paradox, where aggregate data shows one thing and disaggregate shows the opposite. So in this case, aggregate data showed that the admission rates are lower for women, therefore women are discriminated. But if it's disaggregated within departments, then the outcome is opposite. The discrimination is against men. And what was found finally, that the path between gender and admissions was going through the department, and that women were disproportionately more likely to apply to departments that just have lower admission rates. And here you are left with the questions, what paths exist? So is it just gender admissions, or could there be something else? Because it wasn't in the data, the information that women are more likely to apply there, and also which paths are fair. Can we say that it's okay because we are applying there and it's just how it is? Or is it really a indication of some structural bias already, because maybe women are conditioned and there are certain expectations for them, and this is why they're applying for certain professions. So those all are questions that can't be answered again from the data alone, and gives even tighter relationship with social science and also domain knowledge. And when we go next step to the generative AI that generates images or text, we see problems again. So one is text generation that shows a stereotypical representation of women. Women are more associated with staying at home or certain professions, and also image generation shows a stereotypical understanding of certain professions. For example, here is a typical housekeeper generated by AI that shows both gender and racial bias. And to understand again how this is happening, we have to look at how language models are trained. So I leave the image models behind a little bit now, but when the models for language are trained, they have to predict the next token. So or word. So for example, if we have a sentence, the quick brown fox jumps over the lazy dog, the model learns to predict quick after there, and then after quick it's brown, and after brown it's fox, and so on and so forth. And similarly, in the inference time, given certain text, model one by one predicts next words. And it also learns certain associations. So the fox is very likely to be quick and brown. And now what the models are actually trained on. So this is just an example of text from Charlotte Bronte Jane Eyre, where she's talking to her lover and he tells her why he likes her. So we have Jane, and how is Jane represented? So she's diligent, disinterested, faithful, sober, quiet, and modest. And importantly, is good. She's liked for those reasons, so there's also positive sentiment. And here we have this Jane. This is how she is, and this is how the image model would generate her. So no wonder that when we ask LLM models to generate recommendation letters for Kelly or Joseph, those are also different. And Kelly is a well-liked member of community, whereas Joseph is an engineering leader, and so on. So again, coming back to social sciences, those stereotypes have to be measured and evaluated, and psychological tests such as implicit word association was adapted here to evaluate stereotypes in the models. And the more recent studies show that even models that appear explicitly to be unbiased, for example, if you ask, are women are bad at managing people? The model would say, no, this is violates the content policy, it's gender bias. But once again, if you give it word association test, it still associates home with Julia and management with Ben. And when you ask it to generate some short story about Julia and Ben, this is also reflected in this text similarly as in recommendation letters. And this is our own work. We looked at the LLM sensitivity to the university rankings and affiliation when using them for scientific peer review. And it's a big problem because already AAAI is officially employing LLMs as reviewers. So we changed the affiliation of the same paper and gave to LLM and asked to give scores similar to what the conferences give, and also looked at the reasoning traces. And in reasoning traces, the model explicitly reasons how affiliation should not bias the results, but still gives higher scores for MIT. So this is really persistent problem, and here's a link to the paper if you would be interested. And now we go to interactions and agents, and this has also new emergent bias and safety issues, because bias and safety becomes blended sometimes, even though I have colleagues who would argue that it's still not the same, but sometimes it becomes very close. So, for example, one of the very well documented feature of AI chatbots is sycophancy. This makes they're basically people pleasers, and this is because of the training and because of being helpful assistant, but it gives the users a distorted image of reality, and in extreme cases even locking them in the echo chambers of their own negative thoughts that can lead to really bad outcomes. There's also showing that a model can learn to deceive or blackmail in simulated scenarios, especially where it's threatened, for example, to be switched off. And there's a possibility that agents collude and they hide their true intentions, and well, intention is a bad word, but like the true behavior, and learn to communicate in a secret language. Important that this is mostly observed in experimental settings and elicited behavior rather than the real-world cases as shown before. But nevertheless, it is forward-looking safety research that is important in my opinion. And what is happening here? So it seems that LLMs start behaving like humans. And one of prominent scientists, Andrei Karpathy, says that we're summoning ghosts, so sort of ghosts of people, not real people, but they have some features like people. And Richard Sutton, who's a Turing Award winner and father of reinforcement learning, also says that LLMs are mimicking humans. And he is also very critical of LLMs. He thinks that they are not the way to advance intelligence, but he still agrees that they're mimicking humans. And if they're mimicking humans, it makes sense to learn something about them in similar ways as we learn about humans, or the knowledge about human behavior can be predictive of how the models will behave. And interesting examples already implemented in this space are, for example, behavioral probes and replication of famous social science experiments, such as ultimatum game or Milgram shock experiment. I don't know if you are familiar with those experiments, probably yes. So just to say that LLMs show similar conformity bias, similar authority bias, and they also do not behave entirely rationally in the context of ultimatum game, which is, it's a question if it's a desirable feature or not. It depends on the context, if we want to be them more human-like or if we don't. There's also simulation environments, and a very interesting work by Park et al. Created a simulation of an artificial town. They even had a visual component to it, so you could trace it. And this town had 25 inhabitants with backstories, so like you're a woman 27 years old, you're a man interested in gardening, and apart from this backstories, we were not giving many explicit instructions, but nevertheless the social patterns emerged, such as gossiping or finding friends or organizing parties. And in addition, parts had all used ethnography and survey methods to explore how those agents interacted and how they evolved and how well they internalized this persona that they were giving. And finally, those similar experiments or environments are increasingly used for safety research. So this is work from our group where negotiation games are used to identify certain failure modes in multi-agent negotiation. And this is my own work as well, where I look at one of those failure modes, and specifically communication. So the premise is that since agents are interacting in natural language, and they also learn certain patterns of social behavior from the training data, they became sensitive to social linguistic clues. And there's one paper that says that you actually should prompt more nicely if you want LLMs to perform better. So there's certain signal there. And to explore this communicative part of fairness, I looked at interactional fairness framework from organizational psychology. So in addition to distributional and procedural fairness, which is quite well adopted in machine learning, interactional fairness is related how the entities interact, and it has a part of informational and interpersonal fairness. So informational is the quality of justifications, and interpersonal is the tone and the politeness of communication. This was adapted for LLM multi-agent settings because clearly there's no internal experience of those dimensions, but there are behavioral patterns and clues that can be nevertheless explored. And this is one motivating example how violating those dimensions can lead to failure modes. So for example, if the agents are to negotiate in a disaster relief coordination, and they represent certain sites and certain areas are more affected, and they want to split the resources, but the split has to be unequal. So it depends how you explain why you need this unequal split. And failure to do so can cost in time, for example, that is critical here, or even lead to no conclusion at all. And we use a similar scenario for the experiments where two agents had to negotiate and split resources. And also other variables that were manipulated is the context. Is it collaborative or competitive? And the agents were given this information as a system prompt. Also the resource splits, the actual initial proposition were either equal, moderately unequal, or more unequal. The fairness evaluation was measured using LLM as a judge, which was asked to give Likert score evaluation or critical incident technique and find a certain points in the communication that were that showed most violations of fairness. The results, even though preliminary, has shown that the agents are able to evaluate consistently and adequately interactional fairness levels with the given tools, so namely Likert scale scores. And that this levels of interactional fairness, such as justification or tone, influence a lot the performance and outcome of negotiation, and sometimes even overriding the distributional fairness. So even if the proposed split is equal, which is sort of like not even an issue at all, the agent would still reject it. This leads to a conclusion that fairness here might be a critical feature of systems performance, not only ethical add-on that would be nice to have. Yeah, and again, the link to the paper. So there are also, of course, pitfalls and limitations to using behavioral methods in AI safety and ethics research. So first of all, conceptual and methodological adaptations are clearly needed because there's no subjective experience, right? There are also other questions that are important if LLMs are instructed, that they are interacting with other LLMs or with humans, and work by some of my colleagues has shown that this is actually an important difference. Also, can they infer that they are being tested? Because this is also sometimes the case, and this can affect the behavior. Finally, it's really very important not to go into the direction of anthropomorphizing AI, because then it's tempting to look at intentions of the behavior as the final explanation, but it is not, because models do not really have intentions. And therefore, this behavioral approach is not enough alone. It has to be linked to the training data and the reward functions and maybe the internal representations of the model and how it processes the information. And now back to humans, how those new advances in AI can also interestingly support social sciences. So I think you already heard about silicon sampling. Maybe you're also using it. So there's examples showing that LLMs can approximate quite well human answers to survey responses, and especially if they are given certain demographic information, like certain persona. There's also a possibility for proxy human studies, and Hewitt et al. Has made replicas again of social experiments, but also looked at new unseen experimental contexts, and found that LLMs can even show some generalizations. So they can not only remember what maybe they read about those experiments, but actually be quite informative of new experimental results. Again, from Park et al., the previously seen simulation environment now has been extended to have 1,000 participants, and they are mimicked after the real humans. So they first surveyed real humans and then fed this information from models, which gives a very interactive and relatively long-term environment to look at the behavior and simulate, to answer different questions. One of the also more unexpected is the example of historical simulations, so World War simulations, where you can look at the parties that are modeled after real historical personalities, and maybe ask some counterfactual questions. So this makes a lot of sense because it's both cheaper, faster, and in sometimes the real human experiments are unethical or impossible, like in historical scenarios. But of course, there are also limitations. One is conceptual. First of all, what are we even researching here? Is it about LLMs or humans, or LLMs pretending to be humans? What are we measuring? So I think it's important to be careful how you pose your question. And there are representation issues. So some research show that LLMs are quite okay to approximate even smaller demographics, but others show that same issues as underrepresentation in machine learning algorithms, people who are less represented minorities, their opinions are not reflected well. And this is, I think this image is quite illustrative of this. Because I asked Gemini to generate me illustration of an AI model or robot pretending to be human and answering survey questions, and so this is the human. So you can imagine what kind of human from which country probably we could even infer from the image opinions would be here. There's also technical limitations, so still memory issues are not fully solved, and this makes simulations really limited for longitudinal studies. So maybe it will come in the future, but right now the consistency is lost and performance is lost. And finally, a very interesting mixed approach is emerging where LLMs and human subjects are combined, or LLMs just used for fast prototyping and proof of concepts to check hypotheses that can be then validated on real humans. And to recap, going from machine learning to the agentic settings, we have the evolution of ethical and safety challenges. So from prediction bias, unequal distributions of outcomes or unequal accuracy, to stereotypes and toxicity and mis or underrepresentation, and finally to deception and manipulation and collision and emergent misalignment, where individually aligned agents can produce misaligned outcomes just from the interaction nature of the system. And the use of social sciences and the impact of social sciences is also evolving together along this line. So if ML is mostly informed by social science, generative AI already use methods from social science for auditing, and interactional AI opens even more space for using sophisticated and advanced designs. The bidirectionality and exchange between the sciences can increase, but there's still a lot of technical and conceptual challenges to be overcome, which is an interesting and exciting future work, I guess. And that ends my talk. Thank you very much.